Our next speaker is from Fovi3D, previously Rattan software, previously Zebra imaging. Please explain this to us.
My name is Thomas Burnett. I'm the CTO of a small startup in Austin, Texas called Fovi3D. We are a spin-out of Zebra Imaging, and as many of you know, Zebra Imaging has been doing light field holography for almost 2 decades now. And when I mean light field holography, I am talking about the common vision that we see in movies where, matter of fact, I can't even recall a science fiction movie in the past 20 years that hasn't had a light field display at the center of some collaborative effort. Usually it's a battle space visualization, but it doesn't have to be. It could be medical simulation training or what have you. But the whole idea of the light field display is it projects the light that would naturally reflect off an object if it was before you, and a large number of people can stand around the display and collaborate naturally like we would do in a natural light field, like we're doing right now, okay? And so that's our vision. Now, I will say that the avatar display up in the left-hand corner where it projects this ethereal image up here is not what I'm talking about. That is science fiction. But this one down here in the middle where the guy's reaching into the display, that's reality, okay? So if you have direct eye access and you can provide all the depth cues like occlusion, specular highlights, gradient shading, then you will see natural 3D, okay? Why is this important? Well, when we see things in 3D, we understand things quicker, right? We as humans are designed to see things in 3D, and we can comprehend complex situations and come to conclusions faster and with greater confidence. And the best part is with a light field display is after you're having a conversation, you can look into the eyes of the people you're talking to and just judge the level of understanding that they have, right? So if you put on eyewear, that is going to degrade the collaborative experience. So our goal is to produce a full parallax display, large format that can be viewed by a large number of people around the display. We've talked a lot about what a light field is, and the guys Lloyd and John have done a really good job of highlighting what a light field is. And I would just say, look, the Wikipedia page, if there's still any ambiguity about what we mean by a light field, the Wikipedia page is a great place to start. To me, the planoptic function is best represented in what we call a radiance image, which is just basically a very large, and I'm talking a humongous 2D array of pixels where each pixel represents the direction and intensity of light as emanated from a plane, okay? And you can see here I have this little green model here that has a cityscape, and the plane is made up of these what we call hogels, and a hogel is essentially the microlens in a planoptic camera system. So we're actually a planoptic projection system. So instead of capturing light through a microlens array, we project light through a microlens array and angularly distribute that out in a projection frustum, and instead of calling it a microlens, we call it a hogel. And the real difference between a hogel and a microlens array, a microlens or a micro image in the planoptic camera sense, is that we can actually represent data on the other side of the projection plane. And this is really important because this essentially allows us to double our projection depth. So let me just clarify. We can project image above the surface of the display, and we can project imagery below the surface of the display. Now, the ability to do so is largely a function of the pixel density that you can project and your ability to preserve that through whatever optical system you have, right? So the more pixels you have, the more potential you have for projecting with depth, okay? So about a decade ago, DARPA issued a solicitation with Zebra Imaging 1 to develop the world's first light field display for battlefield visualization. And their concept in the solicitation was to make a display that was 6 feet in diameter and that could be viewed by 20 or so people, all bringing their professional perspectives to battle space visualization, okay? So that the commanders could make an accurate determination of what's going on. In phase 1, of this 5-year program, we developed a display that was probably 12 by 12 square inches and projected a viewable image with about maybe 2.5 inches of usable depth. And it was hosted by 60 Mac Minis on 2 Baker racks. And we took this to DARPA Tech, and it was actually a pretty big hit, and it allowed us to continue the rest of the program. If you've ever worked for DARPA, if you miss your targets, they take your funding and it's game over. So we actually did complete all 4 phases of the 5-year program. In phase 2, you know, Baker racks and racks of computers next to a display is not a deployable solution. So they asked us to put everything in the box and make it so that we could actually transport this and drop it into a location like a forward operating base. Okay? And so for phase 2, we ended up making this thing that we called a tile. A tile was roughly a 5-inch by 5-inch, fully contained holographic projection system consisting of the optics, photonics, and all the compute that generates that light field. And by tiling those up, we can make a display that's arbitrarily large. So in phase 3, we made a display that was a meter across, and that's the one that's over here in the blue. A meter across from corner to corner, and consisted of roughly 600, 700 1080p projectors and 81 computers generating that light field dynamically. In phase 4, they asked us to make a color version of it, which meant that we had to do this with time sequential updates to the display, and we made 4 of those prototypes. The UPSD prototype that we finished in 2010 is there on the screen. We made, it's roughly the size of a mini fridge and had a projection output window of maybe 144 square inches. It had 216 1080p projectors and 27 computers in the box. And yes, you could just drop it in place, plug in power and Ethernet, and it was ready to go. There are some videos on our website that you can see the display on, as well as some on how we were rendering. I would just ask you to forgive us. There are some display artifacts, being the first of its kind, the first light field display I'm aware of this type of technology. There's some flicker and there's some non-uniformities, largely because of the photonic solution that we had available to us at the time. This is a diagram that kind of highlights the display architecture. Like any display, the content comes from some application. So there's an application on the outside of the display that formulates some scene from some data stream. So as Lloyd said, the DoD would like to have sort of a static DTED or DEM train with objects flying around it that that they can visualize in real time, and so that's where the sensor data comes in. The situational awareness application in this kind of diagram here formulates a scene, passes the scene over to an array of computers, which generates that radiance image. That is then passed to an array of spatial light modulators, which turn those pixels into rays of light, which then are angularly guided out into the projection frustum by an array of Hogel optics. So this is the system that we have designed. We call it the Gen 1 system, the DARPA system, or Gen 1 system. Our Gen 2 system, which will be available next year, will have doubled the pixel density and just double the projection fidelity, so to speak, to just put a general term on it. Since we're talking about standards, it comes down to how you render. So the big problem is rendering all these pixels. And so what I've diagrammed here is you have a scene, a battle space visualization scene over there on the left. You take that scene, you distribute that to an array of computers, and each one of the computers owns a subset of the global radiance image. And they render those things as fast as they can. And so you require a model, a mathematical description of the Hogel array, and field of view of the Hogel's projection system. And basically, the display interactivity and update rate is directly proportional to the complexity of the model and the amount of compute that you put behind it. There are a couple algorithms I'm aware of to generate this data. Now, as the camera guys were talking about earlier, they're capturing real life light fields. In our situation, we're synthetically rendering the light field. So we take as model an input as model. So in this scenario here, I have the standard Stanford Dragon and my Hogel plane. Those are all those circles there. And what I'm showing here with these blue frustums is that for every Hogel position, I take my virtual camera and I render down, and then I flip the camera and I render up, and I add those two images together, and that becomes what we call a Hogel. That's the data that would go through one microlens in the system. If you were to ray trace this, you would start, of course, with the rays way up here, and then you just shoot through the centers of the Hogels. This is a rasterization technique, so this is not what you would do necessarily for what I'm going to describe next. Is not how you would do this with ray tracing. So I put some pseudocode here. I don't know if you can all see that, but that's OpenGL pseudocode there, where you can render the two frustrums. Now this has a really great benefit, and it renders Hogels directly, which means if you have a serial image writing device like Zebra Imaging's light field, static light field rendering machines or printing machines, then as you render the Hogels, you can just pass them off to the imager, and you don't have to store any of this data. So you render and you write, you render and you write, and you move on. It's great. The big problem is that you're rendering twice for every Hogel, which means you have to make a pass of all the scene geometry up and down for every Hogel to update the whole screen once, right? So this is a big drawback. And by the way, we're rendering in these tiny little frame buffers. So what I mean by that is the directional resolution, the number of rays behind each Hogel, gives you some indication of the quality of the light field that you're going to be generating. So a high-resolution static light field from Zebra will have 512 by 512 rays per 1 millimeter Hogel. Okay? The UPSD DARPA display that we designed had 76 by 76. You can see it's quite a bit lower resolution. So while the Zebra holograms, the static holograms, can project an image with this much depth, our UPSD prototype had about maybe 4 inches of usable depth. Our Gen 2 prototype, like I said, will double that pixel density. It'll add more depth fidelity. If you're interested, I should have quoted the paper. It's a paper by Hale and Cropt. I believe it's called Fast Computational Methods for Full Parallax Spatial Holograms. Anyway, if you want the original article, I'd be happy to give it to you. There's another way to render holograms. This way is what we call oblique slice and dice. And it basically is a little bit simpler in that it uses GPUs more for what they were designed for, which is rendering large frame buffers. And the way you do this is you put a camera at the center of the hologram with an orthographic projection, and you shear it to the direction of a view. And basically, so you would render all the views from that point of view or perspective from from outside the display through the model space. And so again, it's really good for open off-the-shelf GPUs, but it has one huge drawback. Okay, is that it requires conversion from what we call oblique render space to the projected Hogel space. Now, a full resolution, high resolution Zebra hologram will have a terabyte of pixels. So you'd have to generate a terabyte of pixels and then convert that from this space into the Hogel space that we described previously so you could project it. And so this is why we don't typically use this algorithm. This is the slice part of the slice and dice, or the oblique slice and dice. So I render all the oblique views up there, and remember those are all the views from outside the model space. And if I want to make one Hogel, like the upper left-hand corner, the upper left-hand Hogel, I have to pull the first pixel out of every one of those oblique views and integrate them into one Hogel. And I got to do this for every pixel. Every pixel changes space, so I got to move a terapixel of data from one space to another. When I first stood up at Zebra 12 years ago, 13 years ago, this would take 4 days on a 20-node cluster. So back to double frustum rendering. I'm a big fan of using real data when I do my rendering analysis. And so I went off to the Smithsonian collection and I downloaded one of their Jamestown burial scans. These are neat models that they have. And I set up a scenario where I was going to render an array of 50 by 25 Hogels to a 4K monitor, where each Hogel had the directional resolution, the 76 by 76 of the UPSD prototype. So that means that, and I'm going to be rendering this on one GTX Titan, which is a really good GPU. So I have a total of 1,250 Hogels, and I'm rendering Hogels at 100 Hogels per second. It's 100 Hogels per second, remember, because I'm rendering up and I'm rendering down. So I'm rendering at 200 frames per second, but my effective throughput is 100 Hogels per second. And it takes 12.5 seconds to render this model. Now I've done intelligent things with this model. I've batched all my triangles, I've put bounding boxes around them, I've organized it and sorted it, and I would say intelligently rendering this. And I'm at 12.5 seconds per update. So if I extend this to a half-meter display, I would have 250,000 Hogels. And then if I just extrapolate this, it would take 2,500 seconds to render this model for that half-meter display. And generates 1.44 gigabytes per update. So if I want that to operate at 30 frames a second, I'm 30 times that number. And if I want to achieve that kind of resolution that Zebra achieves in the static holograms, then I need to move my directional resolution to 512 by 512, and then I can make a hologram this deep, like you see in the movies, right? The number of Hogel stays the same, but the size of my database, or my pixel data per update goes to 65 gigapixels. Now the funny thing is that the seconds to update the display didn't change, even though the number of pixels is like 16 or 32 times the number of pixels than the previous thing. So the reason for this is that this problem is vertex transform bound. I'm rendering all these Hogels serially by serially streaming GPU commands out to the GPU. Does that make sense? So there's no parallelism in this, right? And the number of pixels I was generating did not factor into this, so I'm not using a GPU very effectively. GPUs are designed to render lots of pixels to very large frame buffers with lots of special effects. Right? So you have massive power in pixel shading, not so much in handling parallel vertex transforms. So many of us that have developed novel display technologies, we develop OpenGL interceptors. You basically hijack the OpenGL stream from an application and you redirect it to your display and you render all the views for your display. But this is inherently a fixed function format, a fixed function thing. You have to know the functions to intercept them and hijack them. And GL has moved away from fixed function to shader-based programming. And shader-based GL is almost impossible to shim with confidence because you have no idea what the programmer is doing in the shader. They could be doing any nutty thing they want to do to get the special effects. But we have to control light. We have to actually, compute the direction intensity of light off that model from a different perspective than the programmer originally intended. And to be able to give ourselves a fighting chance of doing this, we often introduce proprietary APIs to allow us to control that data stream better. And this is why we're here. So we're also associated with Daryl Hopper's lab. We're working on metrology. We're working on SMFoLD. We're working on HVD. We have this problem in spades. How do we make an API that can allow one application to talk to a variety of different displays and not mean that the application developer has to know all the intricacies of that display? Well, one of the big problems, of course, is, again, modern GL is single viewpoint, single viewport, which means that it's inherently not capable of doing multi-view rendering. It becomes the problem of the application or the rendering engine to manage and stream all that geometry to the GPU per view. And this is a problem in stereo. If you want to do stereo, you render once for the left eye, you render once to the right eye, you add those together, you slap them on the HDMI. And for us who are making light field displays, I've got this problem in spades. I got 4,000 Hogels per GPU in my system that I have to render. And the other big problem is, because of the nature of the way GPUs and CPUs are designed today, if I'm hijacking GL and I'm forwarding it over to my display takes 12 seconds to update, it means my host application stalls, right? So the host application no longer becomes interactive. So again, as a developer, I have to know a lot about the display I'm rendering for. I have to know how many views it is, where they should be. I have to know if there's any distortion corrections that need to account for any funky optics that we put on the system. And so it becomes a real problem for us as application developers to introduce novel displays to any kind of environment. So the way I think, personally, that this should be handled is we need to re-architect the graphics pipeline. And I think this is something that Michael Abrush was claiming the other day in his Oculus keynote, was they would like to see the graphics pipeline re-architected a little bit. I would like to see it re-architected so that I could do multi-view rendering as a function of the GPU, not as a function of the application. Which means I want to put a lot of GPUs. Sorry, I can't see this. I can only see this because of these glasses. I can see it when I lean way back. What I want to do is I want to loosely couple the CPU and the GPU, and I want to put the GPU very close to the projection system. I don't want to transfer pixels because you all heard about how many pixels that we have to move around in these solutions. I don't want to move terapixels of data around per update. I want to generate them off a 3D streaming model directly into the frame buffer and throw them away. Okay? I want to put mini GPUs or MVPUs, multi-view processing units, right up into the display, right underneath the photonics, and I want to put a distortion shader in the back end of the graphics pipeline that the host application never knows anything about, right? Matter of fact, the application doesn't know it's connected to an Oculus, a Vive, a light field display, an actuality, a third dimension display, doesn't care. It just throws out the points of view, and the geometry and the display has to figure it out. If I was going to re-architect it, if I was going to do this, I would go and examine the key industries outside of entertainment, because I think that when you look at entertainment, there is a host of other requirements for entertainment. Special effects are really, really critical. But if you look at businesses that do battlefield visualization, or if you're looking at oil and gas or medical, and let me say, if you can do battle space visualization, you can do sports visualization. So whenever I say battle space, throw in basketball or soccer, right? They have the same type of issue. I would examine those and see what the minimum requirements to make a holographic projection would be. And I've listed out what I think they would be. I don't care about special effects necessarily. First pass this, guys. Let's make it simple. I care about natural Phong type shading or lighting, let's just say. Keep it simple. Need one material definition, just do textures. Just do one vertex definition, right? This is probably dozen or 2 dozen commands right here, max, that we'd have to do instead of redoing the whole OpenGL spec. And then I would say, you need to throw in some really intelligent things that applications normally do, and I would push them to their implementation to the display. What I mean by that is, if you're going to pass vertices to the display, you do need to segment them into background and foreground geometry, as some of you guys have called out. If you're going to do the soccer game, you don't need to render the soccer field every update. Just render it once and move the players on top of it. But that requires that the application then specifies what the geometries are. Do they belong in the foreground buffer, or do they belong in the background buffer? And you need to give the rendering engine some hope of attaining interactive frame rates by doing other intelligent things like putting bounding boxes so we don't render what we don't see. Today, that's an application thing. That should be in the GPU. And also in the GPU should be automatic level of detail. If the display is slowing down, then the display should have the option of reducing the level of detail it's rendering, not the application. And I don't want to get into this too much, but you can imagine when you have multiple computers rendering or multiple GPUs rendering all this stuff, there's quite a bit of complexity in the synchronization so that they all update the display at the same time. Here's my vision of the future. I think that the display environment, whether you're sports visualization or medical visualization, will be heterogeneous. That there's not one display that best fits the entire that fits all use cases. For instance, if you're a medical doctor and you're looking at if you're planning a surgery, it's probably best to do it on a light field display. Our light field display is not good for a first-person view. It's great for the God's eye, look-down, collaborative view. And if you're discussing something with someone, that's probably the view you want to have. Right? Remember, you want to look into people's eyes and judge their level of understanding. You want to judge their intent when you're talking to them. Well, you got to look at them to do that. So I think our display is good for that. But if you want to drive the endoscope through the heart, you probably want a first-person view. If you're a tank commander on a battlefield, and you may want that first-person view, but you might want to be directed by someone who has a global view of the battle space, right? So I would like to see an environment where you have simulation going on that can feed multiple display devices. And the application doesn't matter. Matter of fact, you can hook up as many light field displays as you want. You can hook up as many head-mounted displays as you want. And they all can render the right perspectives for the applications that they're designed for. I don't think rendering is going to be in the cloud just because the pixel density is just way too big and that all displays have different pixel requirements. Right? So you put the rendering inside the display, and they generate the pixels off the models that they need. So that sort of implies that everything's going to be done with geometry, that you have to send the soccer field forward, you send all the soccer players forward, and you manipulate everything with handles and transforms. And I think this is okay, because if you do this and you follow a certain couple rules, then you can have displays that update at rates that don't affect the host application. So consider this. You have a soccer game, and it's updating at 60 hertz, but my display only updates at 15 hertz. I don't want to stall the simulation. And as long as I'm not updating the geometry and just sending transforms, then I can actually do that. I'll ignore all transforms that I don't have that I'm not rendering for that frame, and as long as the geometry hasn't changed, let me see if I say this right. As long as the geometry is the same on both, and I send all the transforms, you can make all the transforms you want over here and forward them, and I can ignore them while I'm rendering this frame, and then just grab up the last solid batch of transforms and start rendering that next frame. Okay? Does that make sense a little bit? So I can have independent frame rates of my host simulation, whether it's live or synthetic, and as opposed to what I'm updating on my display. Anyway, guys, that's the extent of my talk. Chuck and I and Mike are over in the back of the room over here if you'd like to discuss this further. Any questions?
That was really deep. I don't think I got all that, but
So it sounds like the display might be required to have a very large amount of memory to cache.
Yeah, so I would say that you at least need the frame buffer memory to hold those images. But I'm trying to not have a lot of CPU memory.
So you could wind up with, well, depending on what you're rendering, you could wind up with a lot of memory.
So yeah, I certainly agree. There's a lot of memory.
so if I understand it, I mean, you're essentially saying it's almost like a pixelated GPU matrix behind the display.
Yeah, exactly. I want to put an MVPU behind every modulation device. And that MVPU just hosts that modulation device, and so that they're not even aware of how many sibling MVPUs that they have. And the host application doesn't care. It just throws the geometry at the display, and there could be a zillion of them. Yeah. The thing is that if you're going to do that, then the data only goes one way. There is no communicating from the display back. Okay, I think that's okay, right?
For some applications, perhaps.
I think it's okay. We'll see.
Hickman?
Yeah, can you describe what the data representation should be for the render view volume?
The render view volume. Yeah, I'm using bounding volumes right now. I have a position and a half widths of a bounding volume, and that defines where the plane is for my display. And so if you want to manipulate the image plane of the display, you manipulate that bounding box. Does that make sense? Or is that what your question is?
No, I wonder if you would use something like a point cloud.
Yeah, so I'm advocating that volumetric data types are very, very hard to render in a streaming fashion, right? They're hard to manipulate. And so I would advocate for a first pass at this. Let's not bite off too much than we can handle. Ignore volume data. And if you're going to render them, they have to be polygonized. Yeah.
So it's basically the gaming model, essentially.
Yeah, exactly. So this works very much like a game does today. I mean, yeah.
Do you intend to imply that each of the imaging devices is a light valve or modulator type device rather than an LCD device?
No, I think the modulation device is really outside of this problem. The real problem is talking from the application to whoever's doing the rendering, regardless of how it's being projected. And right now, when we render for these novel display devices, the application has to know everything about the display. And I would like to break that, right? And theoretically, I just need a model and a definition of some bounding volume to render. And whether you're rendering from the center like you would in a volumetric display or rendering like we do from an image plane, the application should not care.
Micromirrors already require a bit of computation just to operate, but you're not suggesting that be merged with the 3D analysis?
No. Like I said, the generation of the content is whether using micromirrors or LCs or LCOSs doesn't really matter for light field computation, right? That's about the conversion from pixels to light. So you still have the same problem.
Okay, thanks.
Well, we have run into our lunch hour. We have, thank you very much, first of all. So I had budgeted an hour and a half. That means 1:15. We come back for lunch. We're now at 12:15. So I think that should be enough for lunch. So let's try and start again at 1:15 and we'll get back on track.